Good morning, everyone. So my name is Srihari, but you can call me Sri. My background, I'm a mechanical engineer as well. I've been working in medical devices for about 12 years now, but I also have a background in CAD/CAM and in quality assurance. And with my brother, I do some digital health products now, and we're actually building AI into our products. So, there's sort of two different types of hats I wear. At work, I do women's health, and I came off a big project where we, took a redesign and transfer that to manufacturing, and so I've seen some of the pains we have when we don't use automation. And so I'm hoping that this is something that is of interest to people. Because I have 25 minutes in this, it's so little time to cover so many things. I've tried to blog about some of this stuff. I'm also going to upload these slides. I tried to keep the wording on my slides down, but there'll be some footnotes in it after I upload it. So I'm trying to get a jump start here so we can have a discussion afterwards. So we know this, the things that a factory look for never changes. Hopefully the first thing we look for is safety. Then we're looking for the quality of our products. Productivity comes afterwards. And of course, the focus of all of that is profitability. And I'm sure we always want to stay ahead of competition. Whether you automate your factory, whether it's all a hands-on operation, whatever it is, the way you function, these are the primary goals. But from a medical devices industry standpoint, what are we looking for? Obviously, regulatory compliance is at the top of what we are doing, right? Quality is the next thing. But in terms of a smart factory or a smart factory floor or whatever you want to call it, there are other advantages we get. Some of the stuff we struggle with. So, instead of manual data entry, trying to collect automatic logs, automating the production, if you will. And then the other thing, and this is in the example I will give as well, customizing the products for the patient population or the doctors that use them is another big goal. And then of course the integration so that you can handle servicing and CAPA better. So these are sort of the universal goals that drive us towards automation or towards a better factory floor. So just wanted to lay that out. Skip there a little too fast. That was a brief overlook at how we got here. First came mechanization, then mass production with Ford and everything. And of course, we did do automation over the last few decades. So what we are looking at now, what we are calling smart factory today is different. And we call them cyber physical systems, IIoT, so many other terms. And I wanted to see if we can discuss what that actually means for us. So how did we get here? So the way we progressed here is we went from computation. And so there was a recent study that I came across. They claim that 80% of all the recent advances in AI came through the improvements in computation over the last couple of decades. And computation is not just the hardware, but also the sophistication in the algorithms. In fact, if you've been keeping in touch with what's been going on with the Siri and the Android voice and all of that, a lot of that came through deep learning and improvements in neural networks. That came through because of scientists like Hinton, who now works for Google, who did make these advances over the last couple of decades. And of course, we now have the ability to put sensors on everything, so that's been another advantage. And that gives us immense amounts of data. And then the question becomes, how do we analyze this data? And that's where AI comes in. When we say AI, we're talking about general machine learning right now. We don't have the artificial general intelligence. So what does it all mean in terms of the objectives and what we're trying to do? Now, this is not sort of the full set of definitions of what would be a smart factory, but it would have many of these elements: artificial intelligence or machine learning, robotics and automation, human collaboration with machines, that's what I mean there, customization like we talked about, and in some cases novel manufacturing like 3D printing, and then a few years from now hopefully 4D printing, self-assembly, self-correction, that sort of thing. We have that in software now. We will be expecting to push that into hardware. Oh, I am defective, I'm going to fix myself before I get off the floor, right? And then integrated quality control, of course. But if you think that's exciting, that's just today. Tomorrow we'll have artificial general intelligence, something that's able to set its own goals. Instead of us saying, I want operational efficiency, I want scheduling efficiency, I want improvements in this product and that product, it's able to find out what it needs to fix and fix it. You go to nearly fully automation with minimal involvement from us, the sensors will keep getting better. Today, a sensor is hardwired. It only measures pressure, it only measures voltage. Tomorrow, sensors are going to be different. Flexible electronics, they'll have their own intelligence and the ability to change what they measure. And of course, we are expecting other improvements in manufacturing to go along. That said, what do we mean by data? Like, what sources of data can we have, right? You have data coming from your incoming inspection. We already have that. We already do that. In-process inspection, testing, yesterday we had a speaker talking about testing. Testing, is an integral part of medical device design. You can take that data, equipment monitoring, and if you use clean room operations like we do back, so, you're always monitoring your clean room. So you're always monitoring the temperature, the pressure, humidity, particle levels, and all of that stuff. And production data, field data, and planning. One of the things I didn't include is this is a new concept that's taking on is the digital twin. And that's something that, is going to be the future. You'll have your entire factory floor simulated, and you can run simulations on what could go wrong, how things can be improved. All of that data feeds back, right? So this is all sources of data. We have immense amount of data coming in, right, or the capability. So we need something to analyze all that with, and that's where AI will come in. Before that, how would we collect this data and how would we send it forward for analysis, right? That's where cloud computing comes or edge computing comes in. They also call it node computing. Cisco wants to call it fog computing so that they can have their own trademark. What does it mean? You have computation on one side, you have the network connectivity to actually upload the data somewhere else, and the ability to store it so that you can do both short-term analysis and long-term analysis, right? So then the question might come, why don't I just upload everything to the cloud, and why don't I just go ahead and analyze everything all at the same time? Well, you're going to have immense amounts of data. You already have immense amounts of data, whether you're doing the analysis now or whether you plan to do it 5 years from now, 10 years from now. The data is going to be immense in volume and quantity. That will choke your network. And then, it's one thing to expect long-term analysis looking at long-term production runs, schedules, and so on. But what when you need the information right now? So by the time it uploads to the cloud, by the time the analysis is done elsewhere, by the time it comes back to you, it is too late, right? That is where edge computing comes in, where you will use that network connectivity, that storage, that internet within your organization and get a rapid response. You will have a robust set of operations. Plus, think about this. If you're doing, this doesn't exactly apply to medical devices, but for military applications and things like that, they don't necessarily want their data ever leaving the floor, right? So for all those purposes, edge computing has, or fog computing in this case, whatever the name is, that's where the advantages come in. I pulled this example. I was looking for a very good example. I went searching, how there's a lot of hype, there's a lot of articles. So this is an excellent in-process smart floor operations example I pulled off. That's these guys, the DXE people who created the analytics engine for Carl Zeiss. Carl Zeiss Vision Care produces these lenses, and they customize them to order, right? So they have a series of processes. I know it's a little hard. This is my busiest slide, and I apologize for that. But when you download them or you go to that link, which is in the notes, you can see they've described the process. They get the raw material, they form the glass, and then it goes through a series of finishing operations and a series of quality controls. Now, what they did for that factory is these guys set up the analytics and the rules engine, but Carl Zeiss went through and started monitoring everything. They track the labor, they track the production, they track the quality, they track the equipment, the environment, and all of the data allows them to know when the factory is about to fail, allows them to know when to schedule maintenance, allows them to know, how to be able to customize and reschedule and look for operational excellence, right? So this is a current example of smart manufacturing being used in medical devices. Some of the places I've worked at, there's a lot of inertia, and it's like, oh, this doesn't happen in our industry and so on. But this is happening. So tomorrow is already here for us. That's what that example shows us. Wanted to touch base a little bit more on what the possibilities are. So I found this nice example, right? So, there are many things we can measure, right? So we measure them, but one of the most important outcomes of that should be actionable information. That's what we're looking for, and that's what this represents. So I'm monitoring my equipment, I'm monitoring my labor, I'm monitoring my supply chain, my inventory, and all of that stuff. What do I do with it, right? You want to be able to change your maintenance plans. For example, one of the things we struggle with is, how long should something cure? How long should, after I open a set of chemicals, right? One of the things we struggle with is we have all these specially curing adhesives. We just use this blind sort of, we'll open it for 15 days and then throw it away. You know how much wastage is generated by things like that? Or when you stop your machine once every 30 days to do maintenance on it, that's wastage. You may not need to stop every 30 days, and maybe 30 days is too long. So we want to be able to get information up to date and act on it, and that's the purpose of the IIoT, right? And it is not hype, it is already here. We have an excellent booth over here as well. Another commonly discussed problem is, should I go start a new factory or should I go ahead and do an upgrade? And now sometimes you don't have choices and sometimes you do. If you're a startup, you're in a good place to start operations from the ground. You will be using contractors, the components and some of the stuff that comes from elsewhere, but your assembly and your operations will still be in-house. Or if you're introducing new product lines, or if you're creating a second factory floor or a third factory floor, that's a great place to start Greenfield. Brownfield is when you have an existing facility which has its own regulatory approvals, licensing from your regulatory agencies, and you can't really go start a new thing. Then you do upgrades. And then the question is, what are the challenges, right? There's the financial challenges, and they're slightly different but comparable. If you're doing a startup, it's your startup costs. If you're doing an upgrade, it's your upgrade costs. Whereas, what are the uncertainties, right? The uncertainty for a Greenfield is, will this work? Is this the correct way to do something? Whereas for a Brownfield, your uncertainty is that, can this be upgraded? Will this be compatible with the newer technologies? Or is our network so old, it can't work with the cloud servers that we want to implement on our floor? What I'm trying to drive at is that no matter how you look at it, there are no excuses, and the difficulties you're going to have are comparable. So before I switch to AI for a little bit, I wanted to just say one thing. It is very important to know what data you're collecting, right? We can collect a lot of data, but it is important to know what we're doing with it, how we are analyzing it, and also important to know how it can be misused. There are two ways things can be misused, right? Just two of many ways rather. One primary way is you can end up with micromanagers who use this data to do all kinds of stuff. So you got to be careful how to prevent that from happening. I wrote a couple of posts about that, right? But the other thing to remember, and this is key, is security, right? Industrial espionage is just as old as industry is, which means that now that you're collecting all this data, you don't want to put it in a nice package for someone to steal from you and know what you're doing and how you're doing it. So those are some important considerations to think about when we're moving towards a smart AI. So this is one of my favorite slides about AI. I don't know if you guys have come across this story before, but 11 blind men walk up to an elephant. They all touch a different part of the elephant and they come up with a different message. So what I wanted to do was draw a quick baseline on what it means when we say AI in the factory or AI on the floor. If you want just the 32,000 feet overview just for being able to say what it is, it's a discipline where it's a learning system. You always give it data, it learns from the data, and then you apply it. And it happens through computer science where your algorithms come from, and engineering, which is what we do on our floor. This is another slide that just lays out the different terminologies. AI stands at the broadest level. This is from a famous reference text. We don't have general AI. Whatever we define as AI is narrow intelligence, which is basically composed of machine learning, and I'll describe that in a little bit more detail, or representational learning where it learns the features by itself, or deep learning, which is really how we are able to get voices on our phone, machine vision, and all of that stuff now, right? So that's sort of broadly defining the field of AI. And when most people say AI now, when most of the advertisements and marketing materials say AI, they are talking about machine learning algorithms. There's nothing wrong with that. It's a form of AI. So what is machine learning? There is a very specific discipline to it, right? You get the data, which we are already collecting as part of the medical device industry, and we'll be doing a better job of collecting it as we go on. But then the most important thing that a lot of people miss out is the data as collected most of the time is not ready for analysis. This is the biggest challenge in cleaning up the data in what is called labeling the data. Now, if you use deep learning and neural networks, you don't necessarily need to label the data, but for most machine learning applications, you'll have to prepare the data. And that is also where you will have the most time, resource, and expertise expenditure happen. Because once that happens, it's a matter of choosing the algorithms, right? And that is also a trial and error method. You have to pick a series of algorithms. Sometimes you will run multiple algorithms on the same data, figure out what works best for you. But that takes lesser time than actually working with the data itself. Once that is done, we test the data. That is, the idea of machine learning is that you will present the algorithm or the program or whatever you want to call it with new data that it hasn't seen besides the training data, and you still want it to give you insights. And then once it does that, there will be errors and so on. We improve that. That's the basic flow. Digging a little deeper, it's classified this way: supervised learning, which is what, again, most of the current applications do; unsupervised learning, which is what things like neural networks are doing with your phone, voice communications, and so on. And then there's a concept called reinforcement learning, where when it gets it right, you give it a reward, and when it gets it wrong, you give it a punishment. There's an error correction function, and the system corrects itself constantly over time. If you want to think about how supervised learning happens, you want to think about it as data pairs, conceptually speaking, right? You will say, this is my target value, and this is what it needs to be when it is reaching the target value and when it is not reaching the target value. In terms of manufacturing, an example would be saying, if my sensor temperature is between 50 and 60 degrees Celsius, it means that my balloons are being blown properly, for example, or my injection molding is happening at the right temperature and so on. If it is above 65 degrees Celsius, then it is not. So you think of providing the machine learning algorithm with pairs of data on sensors. My particle count has to be this much, my this much has to be this much, and so on. And then from there, it knows what is good and what is bad, so it can alert you. It knows what is functioning, where your process is going wrong, and so on. So that's how supervised learning happens. In unsupervised learning, for example, machine vision, you will just feed it volumes of images or volumes of other forms of data. And what will happen is through several layers, and I'll show you conceptually how that happens, through several layers of looking at the data, the system figures out what those features are and how to improve them. So that's what deep learning is there will be hidden layers. And by hidden, it means we don't exactly see how the features are being discriminated, but eventually it knows how to recognize what is going on. So just wanted to quickly switch to the application side of things, is when we're thinking about, so how is AI going to improve things for me? Right? That's the question we're asking. So there's all this data, there's all this stuff, how is it going to improve? So if you look at automation today, we have automation today in most of what we do. Well, it is basically tediously programmed up front. We know that, right? We program it, we validate it, and we want to run this process for as long as possible without changing it. Because we know that if we have to change it, we have to go through all those revalidations and all that again. AI will change that. It is going to be a learning-based system. So it knows when to correct itself. It knows when to upgrade itself, right? And there is human involvement. We'll talk about that. And the other thing is that today's automation works like this. If there is even a slight problem on the line, there's a line stoppage, and then human intervention is necessary, sometimes even to make minor corrections, right? That will change because it knows, oh, a few things just fell off the floor, or the tool was dulling out, so I'm just going to set aside these 4 guys. It'll just move them along the line, and then it'll change the tool and it'll go forward. So we're looking for those types of applications to improve. That's what the smart factory floor is. That's where AI will be able to improve automation for us. The other way to think about it is that it can solve obvious problems for us. We can ask questions like, improve my operations, show me where my scheduling is falling off, things like that. And non-obvious things, you set it on an observation path, and it's able to tell you which machines are causing the problems to start on your floor, and things like that. Yet another way to think about it is that there are problems where the AI will require human assistance. I don't know if you've heard of this, but the funny thing is this, the things that we would struggle with, AI is able to do really well. For example, looking at thousands upon thousands of images and being able to classify and categorize them, AI can do like that. Whereas basic things that we do, we look at something and we make a judgment call. Oh, that's going to start becoming a problem. This is going to start becoming a problem. AI has difficulties with. So those are some of the different ways of thinking about it. So those are problems. If you did use AI for those things, there's going to be a lot of human intervention required. So for the next 10, 15 years, when you bring these things onto the floor, the left quadrant is what you're looking at, is there will be a lot of human intervention. So all this bugaboo about jobs being taken away and all of that, that's a big discussion. I've written some stuff about it. I've presented about it before. That's many, many years away if that happens at all. Because, whatever intelligence we provide our machines or algorithms with, we still need to train them. Translating our intelligence, you know this. If you've written an assembly procedure, I come from the R&D side, you know how to build something. From that, getting that to other human beings is difficult enough, right? Because that's why design to manufacturing is such a big challenge, is that we have this, the way we do things, we are not able to necessarily get it across that easy. So if you think about another way of how will automation be improved by AI, when you add AI to robots, right, you will essentially be able to change things, right? Algorithmic intelligence will allow the robots to function better and become more adaptable. Just wanted to touch base on these things. Everybody knows these things, but I wanted to quickly run through them. Industrial robotics, we have the biggest explosion, the biggest growth going on, which is the gantries, the universal arms, the custom platforms, the platform beds. And then essentially in manufacturing, we can use robots as well. This is again, I pulled a real life application. And again, something I wanted to touch on, and I pulled this example for that, is that, for example, thermoforming packaging can be automated quite easily, actually, but it doesn't happen that way. So in terms of what are some of the struggles we have, it's going to take many, many years before we are able to actually convince people to bring this on the floor. So that's something to think about. Vision-guided robotics, this has been around for a couple of decades as well. The recent excitement about this is that machine vision, because of deep learning now, is more powerful. And this is where we'll see some of the biggest advances. So some of the biggest advances that we will see first is in inspection, automation of defect detection, and that will come through vision-guided robotics. The other place where we will see vast improvements and probable applications is in exoskeletons. One, it will improve the safety of our assembly operators. So you can see again, it is collaborative, not displacement, right? It is to enhance the people who do the work on the floor, not to displace them. The other way to think about where exoskeletons can be a big boost for your production is when you apply sensors, when they're wearing haptic gloves and when they're doing their operations, you are now able to mathematically translate that finesse, that human ability of how to put something together into actual machine intelligence, right? Because you take the data and you will then be able to automate that for larger productions. This is a big problem where we have custom stuff that has to be done. I'm sure everybody who's done manufacturing has run into this problem. We have a couple of operators who are the only people who can do a set of operations. Nobody else can do it, right? That's one of our biggest challenges. So these are things where the factory is enhanced. It's not diminished by bringing robotics, by bringing exoskeletons, by bringing haptics onto the floor. So that's what I wanted to point out with this example. Where is the future headed? So this is pretty exciting. Researchers at University of Maryland were able to just have their robot watch, and this is a set of videos. I encourage you to go on YouTube and watch this thing trying to cook. If you gave it the right equipment, it's able to just watch videos and learn how to put ingredients together and make things that are tolerably tasteful, right? That's what I heard. I mean, I haven't tasted it myself. You see the advantage, right? We see cooking as one of those sort of non-engineering, very human decision-based activities, and we're able to get the robots to do that, right? So that's what it means for our floor. Because we try to be, right, our goal in the devices industry is, if I give you the device master record, you should be able to produce it without any further instruction from me, right? That's where the robots will be able to help us in the future. I know I'm running out of time, just wanted to touch base on human in the loop, right? This is a concept that, is sort of a thing that promises us great results, but there's also a little bit of a challenge with it, is that, human in the loop is great if we say we are going to make the ultimate decision. But remember, you're going to need to understand how the AI is coming at the decision that it's asking you to approve. and also to be able to do it fast, otherwise we become the bottleneck. And then there's some other stuff I don't have too much time on. Wanted to touch base on this. One of the big challenges is we still don't know how AI makes most of its decisions. So where we want to end up tomorrow is over there on the right-hand side. And let me just leave you with this thought. When we needed to improve transportation, we didn't go about automating the horse. We invented the car. We as humans, right? I'm not making any claim to it. The reality is new technology always scares us, but it doesn't it scares us when it's new. But today we don't think of cars as scary things, right? So it's okay to expand ourselves. It's okay to try new things. It's okay to experiment with newer technologies and bring it onto the society. Thank you.
I think that's great, and it's a great point to end on. We've seen it in our conversations about blockchain, on 3D, on AI, on automation. You're absolutely right, and at the risk of being cliched, the future is here, and we can either embrace it or we can find ourselves out of work,
yes,
I think.
That's true. Somebody said, the future will either roll with us or roll over us. Or we can roll with it or get rolled over.
Sri, thank you very much.
You.
Solid presentation.
Thank
you.
you.